数值到，然后后面最后一场，然后他就说，他就做一个需要参加为什么小动物可能这个比赛的就一个好，而且在我都会觉得可以做事情。第三名，这两个第三名。So are you ready? Oh,
Okay, I think it's time to start. And let's start from so I'm the chairman Zheng Yonghong from Typt University.
And 郑哲可能更简单。
高前专业物理所。
And dear professors, students, good afternoon, everyone.
Good afternoon.
Thank you. My name is Xiangning Lu. I'm from Department of Physics, National Taiwan Normal University. I hope you will enjoy this last number 5. So stay in the last second. Okay. Keep going. Thank you.
Okay, so we should the reporter, opponent, and the reviewer should start your. Oh, sorry. So please introduce yourself first.
Hi everyone, we are HY and my name is Lin Jun and this is Lin Yahui, Chen Hongting and Lin Rongting.
Hello everyone, we are Team Epsilon from Kaohsiung Senior High School, and I'm the team leader Xu Yisheng, Qiu Yude, Wang Ningxuan, Li Haozhi, and Xie Haorun.
Hello everyone, we are team scientists from Jinkai High School, and I'm the Captain Mark, and this is Ollie, Jen, Jennifer, and Ginny. Thank you.
Okay, since the topic is already selected, so please write down your name, the reporter, opponent, and the reviewer.
Keep going.
I'm from Team ATY, and today I'm going to talk about problem number 3, siren. Topic. If you direct an airflow onto a rotating disc with hose, a sound may be heard. Explain this phenomenon and investigate how sound characteristics depend on the relevance. And this one is our experimental device. And this experimental purpose, we want to know the relationship between hose, speed, and sound. We measure the sound and observe its frequency. And this is our experimental device. And we draw a hole onto a wood right here. And we put a model in here. And we stuck the CD on wire and fix the CD and hole onto a model. And then we will change the rotating speed right here. And this is our principle. And we find this principle in official videos. And it's a reflection files as airstream his solid area each hose. Compression wave from as airstream passes through hose. And basically, we blow the straw light here in this picture, and the air particles will be pushed like this one, and then it will stop between the holes. So it will become a air particle burst, and then CD will keep rotating, and then this air particle burst will pass the holes. And air particles will be like this picture. And there are dense part and loose part. And then it will become a longitudinal wave to make sound. And that is why we can hear that. And this one is our variation. We draw 3 circles on this side. 1 and 2 and 3. And their radius is 1.5, 3 and 4.5 centimeters. And then we will draw holes on circles. Like this picture is EZCD, and we draw about 12 holes on this inner circle, 24 holes on middle circle, and 36 holes on other circles. And this is another variation. We change rotating speed, and this rotating speed is we use the tracker to measure that. And this is our experimental flow chart. And first we blow the air to our experiment device with a straw, and we can get the audio files. And then we will put these files into a sonic tool to get audio frequency. And then we will put this frequency into Excel to make chart, and after this phenomena. And this bar chart are 5 different kind of CD, 3 circle frequency. And let's take the most obvious picture. And we can see this line is rotating speed and is low to high. And this one is audio frequency. And as we can see, when the rotating speed is more faster and the frequency is more higher. And then we can see this line is bigger circle and its frequency is higher than small circle. And it is because the faster and the bigger one has more pulse beat passed every second. So it will have a denser longitudinal wave than small one and lower one. And then this chart is show that all kind of CDs outer circles. And we can see this blue line is has 36 holes on the circle, and this blue line has 9 holes on the circle. So we can know that every second will, you can know that if the number of hole passes every second will affect frequency. And this chart showing what we draw the same number of holes on different kind of size circles. And it means that we draw holes on inner circle and middle circle. And we can see this is a very same to the picture. It means that no matter what, big or smaller circles, and its main effect that is just a number of holes. And make a summary. We can know that the main thing affect audio frequency is number of holes, and therefore the faster speed is also mean there are more holes are passed. Last one is frequency cannot be detected. Like here, we cannot detect some frequency because I think that if we use the wrong way to measure that, and it's not scientific enough. Yeah. Thank you.
Thanks for the clear explanation about the topics for the reporters. And I would like to ask some questions for you for your presentation. Could you turn to page 4? So, do you think the reasons that make the sound is the compression wave, as the picture you showed? Yes. Do you think the reason that makes the sound is the compression wave?
Yes.
Yes, let's go through this. Another that I want to please turn to page 10. So do you think the relationship between every graph is a line will have a linear relationship?
Yes.
And so do you think the frequency, when the rotation speed has increased, the frequencies will also increase as a line, as a linear relationship? Okay, so do you think the rotation speed of your model
Yeah.
goes faster?
Yes.
The frequencies will also go faster.
Yes.
Also, another question is, do you think the holes, number of holes on the disk go faster,
Yes.
have more holes on the disk?
Yes.
The frequencies will also go faster.
Yes.
So do you think it will relate it to the compression wave about the frequency?
Yes.
Okay. And another question is, please turn to page 11. So could you tell me what is a line on the graph?
This is this one.
Your fitting line.
Yes.
Oh, okay, okay. Thank you for your explanation. Okay, thanks for the reporter's presentation. And the topic today is problem number 3, siren. And as the problem statement mentioned, that the reporter has to has to explain the phenomena and to find the sound characteristic, which means which the reporter choose to analyze the frequencies about the sound. And the reason that the sound that the reporter mentioned is the compression wave. About the theory, that they mentioned the compression wave will create a sound in different frequencies. And the compression wave will also push the air particles, and that makes the sound in different frequencies and different amplitude. And according to their experiment, the setup they use a motor to control the rotation speed, and they use a disc and plug a hole on the disc to make the various type of parameters. And about the air source, they use the air source that just goes through the disc to create a sound. And about the parameters, they use the hole size, they change different hole size and different locations of the holes, which they create the inner part, middle part, and outer part. And the method they use, they track the rotation speed to control the variables and compare with their to compare together. And they and about the conclusion, they say that the number of the holes are the main factor that make the frequencies get higher, and the size of the holes only make the sound louder, but not change the sound frequencies of the sound. And as the rotation speed rises, the frequencies will also increase. And the reporter also mentioned that the relationship between the rotation speed and the amount of the holes is a linear relationship that I would like to discuss with the reporter for the research results. And about the strings, they explain the phenomenon qualitatively, that they explain the reason that causes the sound is a compression wave. And they have a lot of experiments to prove their assumption that when the amount of the holes has increased, the frequencies will also increase, and about the rotation speed. And here they have clear understanding of the report about the topic that's to create a sound by the disc and the rotation motor. And they have a lot of experiment and use the motor to make the rotating speed controllable and stable in every second. And they use a visual support to let their theory explain clearly that you measure the different pitch of the sound. And for the area for improvement, I think the reporters could do in their future work. I think they could try to figure out some quantitative relationship between their experimental results, since they have mentioned when the rotation speed has increased linearly, that the sound will also increase. And they may introduce more on their experimental graph that I think they have a lot of results, but they didn't. They could explain the results more clearly, and they can add some error bars to let us know if they have do the experiment accurately, and to make a sound absorb box for the noise absorbed. Since that I believe the reporters could do this experimental setup to avoid the sound in a surrounding, and further discuss of the result that they get from the graph about the linear relationship, and I think that will be some curve on the graph, and they can improve their analyze method into some specific method to measure the different frequencies in the single sound. And I think the text film for the reporter will be the partially film, and I think the reporters have a good explanation about the reasons that cause the sound, which is mentioned in their problem statement, is a compression wave. And I would like to start my discussion now. Thanks for listening. Okay, thanks for your presentation. Could you tell me, since your relationship that you mentioned is the linear, so that's can have a discussion at the blackboard. So you say that you have created this and a hold on it, so this is this. So what do you think if you blow the air into the holes on your disc, and when the disc is rotated?
It will find this one and the hole will lie here, and the air will.
Yes, and I can agree to the reporter that they say in a compression wave that when the air goes through the disc, when it is rotated, the air will be cut in a different, will separated in different parts. So if we have a disc with a hole, and the rotation speed will equal to maybe 3 rotating per second, and you have the air result here. What do you think the frequencies will be? Will be the frequency of the sound. What do you think about the frequency in this case? Okay. So So you think that when the results go through the host, the sound will be cut. And the rotation speed has a 3 rotates per second. So in a second, the air will be separated in 3 parts. So 1 part, 2 parts, and 3 parts in a second. So how do you think the frequencies will be in these cases? The frequency of the sound. How many hertz?
30.
Yes, I agree with the reporter that when the rotation, that we find the relationship between the rotation speed and the amount of the host. So, so we improve the cases into a 2 hosts. What will the sound be?
6.
Yes, so we found a linear relationship between the amounts of the host and the frequencies. So in the results that they create, we will find the frequencies will have the proportional to the amount of the host. Is that correct? And in this case, that now we know there are 2 hosts, so frequency will be 6 hertz. So if the rotation speed increased into the maybe 6 rotates per second, what will the frequency be in the 2 host case? 12. Yes, I agree with the reporters about the introduced about the sound frequency, the relationship between the sound frequencies and the relation. So now we know the frequencies were proportional to the rotation speed. Then that if we found the 2 relationship, maybe we can write a simple model about the sound and the frequencies into maybe the frequency might be the amount of the host times the rotation speed. What do you think about the equation here?
Yes, because it's 3 and the whole is 2, so it will be 6.
Yes, I agree with the reporters. And so if we have this relationship, that maybe the reporter can calculate the theoretical frequencies that they can provide in their experiment, and they can have the comparison between the experimental results. That to compare by comparing the theoretical result and the experimental result, they can find if the equation that we provided here is correct. So could you tell me, do you think the sound that you provide will only have provided one single frequency? Or do you think, for example, do you think the wave shape of the sound will be single kind of shape or different?
It will have a many.
Like these cases or this case?
This.
Yes. So in these cases, we can see might be the combined with a different wave shape like this. So maybe that the reporter can have the method that separated this wave shape into maybe 2 different single waves. How do you think about the stuff about
It might be that frequency and sound natural frequency.
Yes, maybe not the actual frequency, but the frequency behind the sound that they measured. And then, how do you think about the flow goes over the flow, the shape about the flow? So do you think, in my opinion, I think when the flows go back part of the disk, it will not completely as the assumption that we made. So do you think the sound will imply maybe a wave shape and we have some surrounded airflow on the track of the ship?
It will have.
Yes. So how do you think about the shape of the airflow that goes through the rotation disk?
It will many air particles, so it will go like this, so it will break.
Spread out and create a sound. So this is the main reason that because the compression wave that the reporter mentioned in their presentation, after creating a different pressure that goes through the sound, the air particles will get through and we can create a different sound of the frequencies. And so another question is, could you turn the page that your problem statement shows? I will believe in page 2. So in this case, So page 1, so that you show your problem statement. Yes. It mentioned that to find the sound characteristic. So what kind of sound characteristic do you think will the sound be like in this case? Maybe you can show the word left of the problem statement, or I will turn the page. Yes. For the last sentence about the sound characteristic, which type of sound characteristic do you think you can measure? Yes. So do you think you can measure maybe the distance for the time in the shape of the sound? So it might be a kind of a characteristic called frequency, the actual frequency in this case. And so for the physics picture that the reporter brought, I think there another thing that can measure as a sound characteristic maybe will be the height of the wave, right? Maybe here it will have this height and another will have a different height. So the height of the characteristic can be defined as the amplitude or the intensity of the sound. So so do you think when the holes get bigger, the frequencies of sound will change?
No.
Yes, I agree with the reporter. So how do you think when the holes is bigger?
And you will sound and will be
Louder. Since the compression wave the amplitude of the compression wave will be louder, right?
Yes.
So the reporter, so in reporter's opinion, which I would agree, that the sound characteristic can be separated in two parts that can be measured. Is the frequency of the sound and the amplitude of the sound. So they mentioned that when the amount of the sound has increased, amount of the holes has increased, the frequency will increase, and the rotation speed will increase, the frequency will also increase. So we can write a simplified equation here. And then the reporter also mentioned that when the holes get bigger, the sound will be louder, which means the amplitude of the wave will also be longer. It seems that the compression wave will be the louder sound that they can be provided. Okay, so where do you place the sound source in the sound that you have many particles in the line?
Yes.
So where do you place your sound source? Oh, okay. So you found sound. You place a sound like here, so you can measure the frequencies under the circumstance on the sound on the outer side. So I think the reporter has then created an experimental setup that they use the different holes on a single line to make sure they can only measure a single hole on the same radius of the disk. Okay, and could you turn the page about your experimental results about the graph? How many times did you do the experiment in a single experiment?
How many times?
Yes.
And one circle, and I will it with about 3 data.
3 data? Okay. And here's all of my question. So I would like to move on to the summarize of the discussion. About the summarize of discussion, with the reporter, we discussed about the source of the sound, maybe the compression wave. And according to the picture that the reporters talk about, the picture I brought, we can figure out the equation that the reporter can calculate the relationship between the amount of holes and the rotation speed. And about the frequencies that the reporter says it can be separated in different frequencies. And I believe that can be separated in the fundamental frequencies or some harmonics about the sound. So the characteristic, the sound characteristic can be measured in the amplitude of the sound that they just mentioned, that when the holes is bigger, the amplitude of the sound will also get bigger. And also the frequencies of the sound can be measured. And about the experiment that the reporter measured, they do the experiment for 3 times. I think they can do more time for the experiment to measure the actual, the theoretical and comparison with the theoretical one.
Time stop.
Okay, want to ask the reporter, can you give me a parameter that many causes the phenomenon?
When the rotating speed is higher and the fluidity is higher.
Okay.
So if you are talking about frequency, we have provided equation here. The amount of the clothes and the frequencies of the rotation speed will affect the result that the frequency is measured.
Okay. And I want to ask the reporter, do you think airflow speed will affect the frequency?
Airflow
Speed.
speed.
Yeah.
And no.
No.
And agree, the reporter thinks the frequency will depend on the airflow that is cut by the disk.
Okay. And will the rotation speed affect the frequency of the sound?
I think it's because the number of coordinates is the rotating speed.
Could you represent your question?
Will the rotation speed of the motor affect the frequency of the sound?
Yes, we have mentioned that the rotation speed of the motor will proportional to the frequencies that we measure.
Okay, and so in your experiments, do you measure that your CD is placed stably when you're doing the experiment?
Yeah, it is very. Yeah.
Okay, and so where did you place your microphone? To
Microphone? No, I like here I point microphone line speed here and you will take the audio files. It's moving now.
can you just repeat that again?
And I put my phone and it's my phone and here.
Yeah.
And I will get the audio files and put these files into Sony tools to get a frequency.
So, did you do the experiments in a noisy is?
No, so I think I don't fix that. So I just need to know the more frequency, not just only one. Yes, I maybe have the background frequency.
Okay, so okay, did your airflow did you measure that your airflow is stably inserted into the CD?
Thank you, sir.
Review.
Please take the floor.
Honorable juries and fellow competitors, this is Jane from Jincha High School, and I'm going to review problem C salary. And here's a summary of the report. The understanding of problem is that the relationship between the size of holes and the rotation speed. And the theoretical analysis is that the air particle passes holes and dance in the amplitude. And the experimental confirmation is that the variables is the rotating speed, the hole size, and the location of the hole. And second is how we record it is we use the sonic tools to get the frequency, and the third one is the compare experimental value, and the fourth one is when the rotation speed gets higher, the frequency will also get higher, and when the number of holes get higher, the frequency will also get higher. And let's talk about the reporter's components. The mergers they have clear explanation and definition of the original cell, and their combined experiment results in quantitative analysis and conclusion. And their possible aspect is that they have lack of explanation of theory and lack of explanation in the error bar, and they should add more explanation in the graph and discussion, and have some discussion part in the experiment result, and they should use FFT to analyze the frequency. So here's a summary of the opposition. The key side of the opponent is that the first one is the airflow through the hole, and the second one is the relationship between the frequency and the number of holes. And the third one is the relationship between the frequency and the rotating speed. And the fourth one is the equation to describe the relationship between parameters to the frequency. And let's talk about the opponent's performance. The merits are that they have clear summary of the reporter's report, and they give good advice to the reporter. They have clear explanation about theory, and they have clear explanation about the frequency. And their possibleness that is they can talk they can have more discussion on experiment data. And let's talk about the discussion part. The first question is that in this graph is that linear relationship, and the reporter says yes, and the reverse views is that we can convert the trend will be linear, but it has a proportional trend. And the second one is the relationship between the frequency and the rotating speed and the number of holes. And they have an equation, and the reporter agreed. And the next question is that does airflow speed affect that? And the reporter says no, and the opponents agreed with the reporter. But and the next question is that will the rotation speed affect the cells? The reporter says that it won't affect, but the opponent says yes, and I think that it will affect. And here's a general suggestion. I think the reporter should use FFT to analyze the frequency, and they should add some convincing theory. So thanks for your listening.
So, reporter, please.
That is during the discussion with the opponent, and I think me and opponent and reviewer and is all agreed that frequency is equal to the number of holes multiply the rotating speed, and I think that given to take out the background frequency to draw the chart line is my fault, and I will fix it that future. And I think yes, there is not only a frequency in the I measure that, so we need to know that the more frequency in the sound.
So now open for the question on the screen.
11. It seems that all three of you agree that F is equal to N times omega. But could you check if this is true from this data?
It's not very clear like that. It's because I think I don't take out the background frequency, so it's not the clear frequency like that.
The x variable is radian per second. The unit of the x variable is radian per second.
Yes.
Yes.
If so, then 360 degrees is about 6.28 radian.
Yeah.
So if it is 20, then it just about rotates 3 times per second. And then if there are 12 poles, then that's each second there are about 36 holes. But your sound frequency is much higher.
That means that my frequency is not very clear. Like it need to show that because it will add some background frequency or another frequency. Not just only the whole of number like that.
So based on this data, do you
I think the relationship that we discussed is qualitatively about the physics teacher that you brought about, that the frequencies were proportional to the amount of the holes and the rotation speed. So I think the radius per second, I think the rotational speed per second will be clarified about the relationship that if the reporter, I suggest the reporter can change the unit about the rotation per second, that it will, I think it will fit the simplified equation that we provide.
So you think it's better to write a perpetual
Yes.
decimal?
Or we can add a constant, maybe to create an equation.
If you comment on this point here.
In this point, I agree with Kim.
Okay, I have a question for all of you. So according to this figure, is there any cut of frequencies or cut of speed that you cannot you cannot make any sound? Is there a lower limit of the rotating speed? And also, if you do a linear fitting, there is an intercept. According to your fitting, I think that the intercept around 0 would be negative. So is it reasonable? So, reporter.
You mean that why?
Okay, first, is
Yes.
there any lower limit of the rotating speed that you could not hear any like it?
Yes, and like no, and actually I try to that is rotating like that, but if I change the ampere like that, then it will stop. Like yeah.
Okay, thank you. So about exponent.
I think the limit about the frequency that can measure, or maybe under the circumstance that the rotation speed is too small, or under our cases, the frequency that we measure should be only the 6 Hz. That I don't think the measurement about the audio film can analyze the frequency that under some certain frequency. And another is that when the frequency is higher for some specific volume, so about the human air, that there are some specific range about the boundary that the human ears can hear. So for the microphone they use might be to have some range that they can record the sound.
3, 5, 6, 5, 5. And for the opponent, 5, 6, 9, 8, 7. And for the reviewer, 6, 6, 7, 7, 6. So now it's time for you to prepare.
Hello everyone, I'm Ashley Wing from Typt. Today I'm going to talk about problem number 1, fractal finger. So here's the problem statement. The effect of fractal fingering can be observed if a droplet of an alcohol mixture is deposited onto dilute acrylic pen. How the geometry and dynamics of the fingers influenced by relevant parameters. So we main focus on 2 parts. The first one is the geometry, which is the different fractal extent and looks for the fractal fingers. And second one is the dynamic. The growing speed, length, and area of the finger should be measured. And here's the observation video. First, there will be a constant diffusion moving from the center. And then, while the diffusing, the fractal fingers start to appear, like the observation video shows. And then, it keeps spreading until the diffusing and fractal motion both stop. And both stop means when we watch from the camera, and we think the fractal will never stop. So here's observation. We separate it into 3 parts. And now let's talk about problem statement. So the problem statement mentioned that we have to use a alcohol mixture. So we found out that alcohol is very crucial to be added into the mixture because the ink-water mixture cannot have the fractal mode. And also, we tried different proportion of the alcohol-ink mixture. So then we found out when adding more alcohol, it becomes fractal. Like the video shows, this one is much more fractal than this one. And also, the problem statement talked about diluted acrylic pen. So why is the problem statement mentioned the diluted acrylic pen? So we found out different proportion of the water and acrylic pen. So we found out that if we add more water, the finger will be longer and more complicated. And here's different dropping speed. We also measured different dropping speed. With that, we found that the dropping speed is faster, the finger grows faster. Like the left-hand side one, this is the faster one. And now let's define the fractal. It is very important to define fractal because the problem statement mentioned the effect of fractal fingers can be observed. So what is fractal? The left-hand side is the simulation of fractal that we found on the internet, and it's just a simulation. And this is our experimental result. So we define a fractal as a geometrical shape that can have self-similarity in different scales. Like fractal fingers can be described as a finger's finger. So we separate the 3 phases, which is diffusion, fractal, and both stop. And diffusion start with the gravitational effect, the Marangoni flow, and when the surface tension becomes the same, it will stop diffusing. And the fractal is because of the segmental instability, which include one of is the perturbation, and the other one is the viscosity difference. So now let's talk about the diffusion. It starts with the gravitational effect. So surface tension isn't strong enough to hold a droplet. So droplet will be like the right-hand side picture shows. Because of the gravity, a droplet becomes flatter. And because of the thickness difference in the middle and the side and the rim, so it will affect the evaporate rate of the alcohol and also have different surface tension. So it will cause a Marangoni flow, and Marangoni flow keeps appearing from the center. So when the diffusion ends, that means the same surface tension. We can calculate in this picture that when the surface tension between the air and the mixture times the angle plus the surface tension between these 2 media times the angle is smaller than the surface tension in between these 2 media, and it will keep diffusing. However, if the equation is equal, it will stop diffusing. And let's make a comparison between the Helen-Shell cell and the experiment. So Helen-Shell cell basically is inject a water into the alley between 2 acrylic pen board. However, we don't have the board both, so we change into the air pressure. And we also gave a initial velocity that the Helen-Shell cell didn't have. So we mentioned, so we defined it as U0, and we will talk about in the later the formula. So here's the Navier-Stokes equation that we can use in this situation because we define our experiment a Newtonian float, so it can be used in this equation. And also, these three equations will be included in our calculation. The first one is the continuity equation, and it's for incompressible flow that is able to use in our experiment, and also the Darcy's law, and also the convection diffusion equation. So here's the segment-Taylor instability, which we include the Darcy's law, and the Darcy's law is because the incompressibility of the flow and the Darcy's law with the constant this, and to be determined by continuity of pressure. It gives out the unperturbated pressure field like this. And here's our process of calculation, and we finally got this equation. However, when mu2 is bigger than mu1, it leads to the growth of the perturbation, so we add a recited number here. And we finally got our equation. So here, this is the initial speed and the viscosity difference, and add up the viscosity. So here's our simulation by using COMSOL. So here's the operation screen and the parameters. So in COMSOL simulation, we simulate a two-dimensional display which surface tension has been involved. And here's our experimental setup. So I think the most important part is the pipe T. The pipe T can control the amount of each droplet, that the droplet will be the same amount. And also, this is necessary to use a constant temperature bath because the viscosity will be affected by different temperature. So we use a constant temperature bath to maintain the temperature of the acrylic pen and the water-based ink. And let's talk about our experiment. Our first experiment about the concentration of the acrylic pen, which is on the board, and we will measure the different extent of the fractal as clean or blurry, and also the maximum depth and growing speed. So here's the COMSOL simulation, which R is defined as the difference between two viscosity. And here's the simulation result. So when R gets bigger, the fractal gets longer and more complicated, like the simulation shows. So let's make the comparison between our experiment and the model. So the growth rate can be shown like this, and in this situation, the recited number can be ignored because it's too small, and the difference between the mu2 that we'll calculate later. And here's the comparison. So when we add more water, we will find that it becomes blurry because the water diluted the finger. And theoretically, it should be simple to complicated. However, because the water diluted the finger and the rim, so it will become simple again. And the complicated one is in the middle. And also, we analyze the maximum depth of the finger, which is the red one minus the blue one. So we analyze the data by image and analyze the maximum of the length of the finger. This is the chart that we have. And we found an interesting question that why is the error bar here gets bigger? Because we assume that the water dilutes the end of the finger, so it depends on how much ink goes to the fingers. And the finger will be diluted by water, so it will difficult to calculate. And we also analyze the growing speed. And it's the orange one minus the blue one. And the orange one and the blue one. So we will focus on the right-hand side. So when adding more water, growing speed gets faster, and growing speed between the rim and the center gets bigger, like the yellow and the blue is getting bigger. And we have a comparison with our experimental result and our theory. We found out that the equation really fits our theory, like the chart showed. And also, we did an experiment about the concentration of the in-alcohol mixture, which is the mu1. So we will measure the geometry. This is the important part of the problem statement mentioned. And we will also measure the growing speed. So here's geometry of the fingers. We separate it into three parts. The first one is irregular ring. The second one is the flower-like ring. And the third one is the fractal finger ring. So that we found out when alcohol to ink is 5:1, it fits our definition of fractal, which means there will be a finger growth from the finger. So there's comparison between the experimental and the theory. We found that the ink-water mixture cannot have a fractal finger because it skipped the Marangoni flow and because no evaporation of the alcohol. And we analyzed the speed of the droplet as the same way as the last experiment. And we found out that since the magnetic flow is caused by different evaporate speed of the rim and the center, so the 2 to 1 will be not very significant. And also, the 2 to 1 part is not able to have a fractal finger in our experimental result. And also, we have different speed of the dropping droplet, and it's the U0 we mentioned before. And we also measure the speed of the dropping droplet as the same way as the experiment before, and we found out that since the growing speed is positive correlated to U0, so when dropping speed gets bigger, the growing speed of the droplet will also be faster. So then we found an interesting point is that the between these 2 points and these 2 points and this 2 points, it becomes smaller. So what is it? Because of the growing perturbation and also the recited number we mentioned before, it will cause the decay of the placement between these two. And also we compare with the console. We found out that the theoretical model and our experimental is really big. So now let's make a conclusion. First, we talked about our theory. We separated it into 3 parts, and we talked about the diffusion and the fractal fingering, and we also gave a formula right here. And we also did the experiment about the concentration of the acrylic pen. When adding water, fingers go clean to bury. And we also find out the complicated one, the complicated concentration. And we also did an experiment about the concentration of the ink alcohol mixture, which is the mu1 upside. And since the alcohol to ink is 5 to 1, it fits our definition of fractal. So the picture can, the chart, the experimental result can be shown like this chart. And also, we measure the dropping speed of the droplet. We found out that when droplet speed gets bigger, the growing speed gets bigger, and also the area of the the fractal finger also gets bigger. So here's the end of my presentation. Thank you for listening.
Okay, thanks for the reporter for her report. That in these 2 minutes, I'll have several questions to ask the reporter about. So the first question is that so you admit that there is a ring on the geometry.
Yes.
Okay, and second question is that do you have a boundary condition that doesn't form a fractal fingers?
A boundary condition. When the alcohol to ink is 4 to 1, it's not gonna be fractal. So we show our chart starts from 5 to 1. They can have a fractal finger.
So next question is that have you have an explanation of the geometry growth?
Yes, we separate into 3 parts. The first one is irregular ring, the flower-like ring, and also the fractal finger ring.
Okay, and next question is that, so you see this phenomenon as a non-stop phenomenon?
Yes.
Okay, and next question for you admit that the dropping speed have a positive correlation to the speed of fractal fingers?
Yes.
And what are the parameters of the phenomenon that it affects the most?
Affect the,
like surface tension or concentration?
I think it's the difference between the viscosity.
Viscosity,
Yes.
okay. And next question about the, what do you think is the main, the most important factor that determine the motion of the phenomenon?
Determine the motion. I think it's the segment-Teller instability. That's called the fractal.
Okay, so as I see in the experimental setup, so you think you need to maintain the temperature for the whole experiment?
Yes.
Okay, and you think that your console simulation can fit the real condition, right?
Yes, it's really similar to our experimental result. And it's, we set the old condition the same, so we believe that can be comparison.
Okay, thank you.
Thank you.
Honorable juries and fellow competitors, I'm the opponent from Team Scientist, Tsingshan High School, and today I'm going to opposing the problem number 1, fractal fingers, which the problem statement is focusing on a droplet of ink alcohol mixture and deposits onto a dotted acrylic paint. And we need to investigate how the geometry and the dynamics of the flow. So here is our main two focus. And about the reporter's structure, that she has a observation video about the ink alcohol and the acrylic paint, and also the dropping speeds observation video. And in a theoretical model, they have defined the fractal and also the diffusion rate and the header-show cell they apply into their theoretical model. And about the setup, they use peptides and also constant temperature bath that may maintain the temperature of whole experiment. And about the experimentation, they have done the research about the concentration, maximum of finger, and also growing speed, and the geometry of the fingers. And in the conclusion, they give us the growing rate and also the comparison between the experiments and the theory. And here are strong points and weak points about reporter, which the strong points contains the clear definition that they have defined the fractal in a clear definition. And the second is that they have compared with Comso's fluid simulation. And third one is they compare the theory and the experimentation together and see the results. And they can explain the experiment results clearly. And about weak points is that they have like explanation in a coefficient in the theory part, and they don't have detail about the experimentation explanation. And here are some points that I'm going to discuss in a further discussion, where we will start from the observation of the ring geometry and the outer diameter of the ring, and also the experimental setup, which is the acrylic paint's geometry. And the theory part will talk about the vapor rate and also the dissolve of the paint with between two fluids, and also the velocity and the surface tensions cause the results. And the experimentation part will talk about the boundary condition and also the graphs they have drawn and the simulation and also the definitions of the fingers. And next move on to the discussion point. So for the opponents, that the first question I would like to ask the reporter about in your observation. Can you show that?
This one?
Yeah. We can see that there is a white ring in your observation. Can you explain that?
Okay,
Maybe
that's
it's
me
because
by a
concentration.
backup page.
or-
Wait a minute.
Yes.
Okay, so we have observed this kind of phenomenon, and it's different to the console simulation. So we have three kind of explanation that can explain this phenomenon. This one, yes. The first one is the surface tension causes the cohesion, because the cohesion, so the ink and the mixture make cohesion like this, and also because we maintain the acrylic pen very thin, very flat, so it may stick on the board, or the console simulation is a two-phase flow. However, in our experiment, it should be the three-phase flow. So there might be a white ring right here. That's our explanation.
Okay, in this problem, that the opponent agreed with the reporter about the cohesion caused the main about the white ring's geometry. And so since this problem is solved, then let's move on to the observation that you can see, yes, from
Oh, wait a minute.
the
This is
observation.
Observation.
Yeah, that there is some deviation between the upper ends of the outer diameter of it, and it seems that the upper side is bigger and the downside is smaller.
Oh,
Do you
you mean like this is more outer and this is more inner?
like the outer alter the ring that the length is bigger and the downside is
Oh,
smaller.
okay. Since I mentioned the contribution in my theory, I think this may caused by the contribution, and it's also the reason why caused the fractal. And also, I think there's another kind of explanation, like if a droplet is like this, and if it is not uniform, maybe the concentration of the Marangoni flow will not go the same in our experiment.
So the contribution caused the main deviation. So that may lead to the next problem is that, so in the, how do you make your acrylic paint that for your experiment?
Acrylic pen,
Yeah.
well, we try our best to make it very flat. However, it still will be some little, like, it's not pretty flat. And in this part, we think we can include this into the perturbation of the experiment.
So in the opponent's view that we think the main contribution will be caused by the geometry of the acrylic plane.
Yes.
And is there any factor except for that the reporter think?
You mean about the
Yeah.
flat?
The contribution
Perturbation is the
It's
perturbation.
only caused by the acrylic.
And also I mentioned before is the maybe the droplet is not uniform. It
Not
may cause
uniform.
the perturbation.
So let's move on to the next question, which can you please turn to page 12?
Yes. Sorry. It's right here.
And since you said that the middle, the evaporate is slower and the evaporate is faster in the outside, that can you explain why if that evaporate will be different?
Okay, so right here it is thicker, so I think it will have evaporate slower, and here it will evaporate faster, and because of the evaporate rate, it will cause the different surface tension that cause the Marangoni flow, and because the water's surface tension is larger than the alcohol, so right here, if it evaporates slower and the viscosity may be, the surface tension may be lower, and right here it may be higher.
So the main cause of the surface tension gradient is because water's surface tension is bigger, right? So
Yes.
when the evaporate is faster, then they will have higher surface tension in opposite
Yes.
view.
Yes, I agree with that.
So in this part that the reporter agrees with the opponents, then let's move on to the next question about, do you have a kind of quantitative results that you can explain this whole experiment?
We have observed the length of the fractal finger. However, the reporter mentioned that we think the fractal will never stop because if you use a microscope, maybe the fractal will still be like fractaling. So in this situation, we're not going to have a accurately number of the fractal finger lengths.
Okay, in this problem that the opponent agrees with the reporter, which in the ideal model that the fractal fingers will never stop. And next move on to the next question about, could you please turn to page 13?
13. Oh, sorry. First. This one.
That, so why is there the alkali mixture have another surface tension? That is it because of the mixture of the alkali paint and the ink alcohol mixture? So the surface tension will change.
The surface tension
Will change in the downward side. That.
Oh, you mean this one? We have due to the fractal finger have to these two kind of liquid, which this is the ink alcohol mixture and this is the acrylic pen. So these two have to it can be dissolved together. So we can assume here's the surface tension like this, and this surface tension is between the acrylic pen and the ink alcohol mixture. However, the up one is the between the air media and the ink alcohol media. So if we see the surface tension as a vector, like in this side and this side, and we can times the angle, that we can have this kind of formula.
Okay, in the question that the opponent agreed with the reporter that there will be 3 kinds of surface tension, and the problem is solved. So let's move on to the page 16.
Page 16. Sorry. Right here.
So you can use this model in the phenomenon for the calculation of the
Yes,
speed of.
we believe it can use in our phenomenon because a droplet is a Newtonian fluid, so we can use it in this situation.
And the opponent agrees with the reporter. Then let's move on to page 19.
19.
And
Right here.
I would like to ask about the viscosity constant that
You mean the
mu2 and
this one?
mu1. Yeah, that. So what will happen? What if the mu1 is larger than mu2?
mu1. Well, we didn't measure, we didn't consider the situation if mu1 is larger than mu2. Maybe there won't have a contribution, but however, we didn't consider this situation because if mu1 is larger than mu2, and we think the fractal finger will not happen.
So it's kind of a boundary condition of the reason for forming the fractal fingers, right?
The boundary? I don't think so. I think the boundary may have the boundary concentration. However, this is just the condition, the needed situation that the fractal finger have to be observed.
Okay,
Can
so
be observed, yes.
this will be the condition, but not the boundary. Okay, in
Yes.
this part, the opponent agrees with the reporter, and so I would like to ask another question. Is that why do you maintain the temperature during a whole experiment?
Okay, so as we know that when temperature is higher and the viscosity will be lower. So if we don't maintain the temperature, the viscosity is the main factors that may affect the fractal fingers phenomenon. So we have to maintain the temperature and also maintain the viscosity of the acrylic pen and also the ink alcohol mixture.
Okay, in this part, the opponent agrees with the reporter, which we need to control temperature as a control variables that won't affect the whole experiment. And that's the next part. I'm going to ask that what kind of model does your console simulation use?
What kind of model? We mentioned these 3 equations in right here. So in the console simulation, we tried our best to simulate the real situation to the computer simulation, and we use the coefficient right here to maintain the situation will kind of be very same.
Okay, in this point, that opponents agrees with the reporter that they use a complex model for simulating a real-time, real-life situation. And so, about your console simulation, that
Yes.
there is no white screen in your observation,
Yes.
can
We
you
also
explain?
mentioned that. And in the first question, because the console simulation is a two side.
Is it two-phase?
Yes,
fluid?
2-phase flow, and
Oh.
however our experimental is a 3-phase flow. So that may cause the white ring, and maybe we can have some future work to make the console into the three-phase flow in the simulation.
Okay, my question is over.
Thank you.
Yeah, in the summarize of the discussion that we first start from the geometry of the fractal fingers, and we discussed about what forms a ring in the observation, that is the contention force in the fractal fingers. And then we move on to the diameters difference, which there will be some contributions in the experiments that will cause this deviation of the outer diameter. And also we also discussed about the surface tensions and how to define them and how the temperature will affect the viscosity, and we need to control that during the whole experiment, which is very necessary. And finally, leads to the console simulation, which they use a complex model for the simulation, which is great. Then this is my summary. Thank you.
I want to ask, did you think that the referencing finger is like a part or a base part like?
Well, the definition of fractal finger we mentioned is like here's a finger of this phenomenon. However, it's not a fractal finger. It must be the finger that grows from a finger that we call it a fractal finger.
Yeah, but it was like one and plus one.
Oh no, I think it's just one layer and it will become thinner and thinner, flatter one. Yes.
Another thing about that, you put it the ink inside the then will lose and you will like drop one or into the ink. Not the ink high of the main of the
Which I agree with the reporter said that their fractal fingers geometry will be like that.
Here is kind of phenomenon again.
Well, the phenomenon is caused by these two main factors. The first one is the diffusion, and the second one is fractal. And diffusion is caused by the gravitational effect, then the Van Gogh effect, then it will come to the same surface tension as the diffusion. And how about the fractal? And the most important one, it is because of the segment-Taylor instability, and which includes two parts. The first one is the distribution, and the second one is the viscosity difference that may cause the fractal finger in our phenomenon to appear.
And do you think that alcohol just a high or a many high alcohol can do this experiment?
You mean different concentration or
Yes.
what? I think we mentioned in our experiment, if the ink alcohol is 5 to 1, it will be fractal in the experiment 2. Wait a minute. Here. So if the alcohol to ink is 2 to 1, it's not going to be the fractal finger. So it has to be a certain, upper the certain concentration that can have the fractal finger to appear.
Okay, so you.
Okay, this is the review, and today is talk about further thinking. And first, the opponent asked the reporter that and the topic is that the afters of the control fingers can be observed if a drop of ink alcohol mixture is deposited onto the plastic pen. How are the terminal and penalty of the finger influenced by relevant terminal? And its main focus are what? And main focus is a different factor in hand and those of fragile fingers. And the limiting the growing speed area of the fingers and conclusion, when adding water, fingers go into break. When the dropping speed goes up, pouring speed goes up. In the equation, when R gets bigger, the finger gets longer and growing area, the great rate comparison between the experiment and the theory. And discussion one, opponent asked what the main important. And discussion two, opponent asked how can you make European flags? And reports say we try our best to make it flat. And discussion three, opponent asked explain why investor is different. And if reporters say because of the different surface attention. And discussion four, opponent asked either state a reporter slower, also finger incorporate faster finger never stop, and reporters say that faster finger will never stop. And discussion five, opponent asks different surface tension, can you use model to explain the phenomena? And reporters say yes. And discussion six, opponent asks why maintain temperature, and reporters say to maintain viscosity. And discussion seven is read is the ventricular part and reported that it's just a fluid that's just going to be used. Thank you.
So, reporter, please.
Okay, so thank you for the opponent and the reviewer. Here's my concluding remark. So first, I'm going to talk about my discussion with the opponent and also some points that in my presentation. So here's my highlight. So we investigate the geometry of the fractal finger by using imaging to analyze the length of the finger. And for dynamics, we use the tracker to find the growth speed of the finger. So we think that it is pretty appropriate to the problem statement because the problem statement asks us to investigate these two kind of parameters. And we use the console to simulate the fractal finger to comparison with our experiment. And the opponent also asked this question about us, and we figured out a good way that we can change the console from two-way form to the three-way form. And we investigate the reason that caused the diffusion and the fractal fingering by separating it, and use the fatigue to control that every single drop is equally, and also the temperature fast. And here's our discussion points. So first, a discussion with the opponent, and the opponent and the reporter has the discussion about the geometry of the white ring between the fractal finger and the rimming part. I think this is pretty important because the simulation and our experimental results just have this kind of difference. And we solved this problem with three kinds of explanation: the cohesion, and also the ink well stuck on the board, and also it's because it is one kind of two-phase flow and a three-phase flow. And we also discussed the relationship between the simulation and experimental result. We discussed about the temperature bath, since the temperature is one of the important parameters that we mentioned in our equation, and the temperature may affect the viscosity of the liquid. And also we discussed about the Marangoni effect and the evaporates be in different position. Thank you for the report, the opponent and the reviewer.
That's a very short question. Is a acrylic pen made for using the pen?
Pardon.
Is an acrylic pen weight?
Okay, so the opponent asked about this question, and I think we try to keep it pretty flat. However, it's still
Is it dry or it's wet?
wet because it's acrylic diluted acrylic paint in a polysilicon.
So what do you feel wait till it's dry? And,
Sorry.
what do you feel wait till it's dry? And then do it. Is there anything?
If it is dry, I don't think we will. This kind of phenomenon will happen because in our phenomenon observation, we also find if we add more water, the finger will become dense and it will be complicated. Thank you.
Okay.
Okay.
Reporter, in your Cosmos console simulation,
Yes.
there seems to be much more parameters you need to fill in,
Yes.
like the phosphorus of the material.
Yes, we include the you mean well, you mean the porosity of the medium?
Yeah.
Yes, we also calculate the porosity of the medium in our COMSOL simulation. However, we didn't fix out the two-phase flow to the three-phase flow, so that's our area for improvement. However, we also calculate the porosity of the medium in our COMSOL simulation.
You measure it or calculate?
We found on the website that it has the acrylic pen have a certain range of the porosity of the acrylic pen. So we.
So I have a question to the opponent. On page 5, you talk about the boundary condition. What is the meaning of the boundary condition for?
In my opinion,
Your
it's
opinion,
like a limit of value that will determine that this phenomenon will grow from the smallest phenomenon to the highest phenomenon of the boundary condition. It's kind of like a limit of.
Oh, okay. Thank you.
Okay, I have a suggestion for the reporter. Since you did a series of experiments,
Yes.
so can you figure out or can you plot something like a phase diagram that gives us some critical values for your parameters?
Okay, so first, we talk about the length. I think the length is not able to calculate because the fractal will keep growing, so we will not have a critical number. And the things that we didn't calculate by our formula because we are not, we don't have the equipment for volume the viscosity of the liquid, so we didn't calculate it. But we tried our best to comparison with the theoretical line. Thank you.
So for the opponent and the reviewer, do you think that is there some important parameters or missing parameters that can give some critical value?
Well, in the opponent's view that we think we proved with the reporter that the length is a very important parameter, and which we can also lead to the velocity and the discussion of the investigation of the dynamics of the fractal fingers.
Thank you.
So for reporter is 6, 8, 8, 8, 8. Okay, sorry. And for the opponent, 6, 7, 8, 7, 8. And for the reviewer, 4, 5, 5, 4, 4.
交通都会有受到影响。
Okay, I think it's time to start the run. And reporter. Okay, so please write down your name.
Honorable jurists and fellow competitors, I'm a reporter from Scientist Xinjiang High School, and today I'm going to report problem number 12, rice kettlebell. And here's the problem statement that we can look at take a vessel and pour some granular material into it, for example, like rice. So if we dig a spoon into it and at a certain depth, which is very important, certain depth of immersion, you can lift the vessel and contents by holding the spoon. So we need to explain this phenomenon and explore the relevant parameters of the system. So here are three main focus. That first one is explain why the vessel will be lifted, and also the significance of granular materials in the experiment, and also relevant parameters like diameter and grain size. And there are observation video. Then today's content, we're going to start with observation, and then come to theory, and also the experimentation, and then finally leads to the conclusion. So about our observation, that we use a fixed pulley on top of the force gauge, which can measure the 1 grain for the minimum, and to use it to pull a force on the rod, that the rod diameter will be the 0.66 centimeter, and there will be a wooden stand on top to fix the rod, and also the grains we use are the glass bowl for diameter 1 millimeter, and also the rice for 2.64 millimeter. And we use 3D printing vessel to control the diameter of the vessel. And before our experiments, we'll shape the vessel to control the zinc packing fraction by average of the 0.638, which we'll explain later. And here's our quantitative explanation, that when we apply the force on the rod, that applied force will cause the particles in the material to rearrange themselves to a more ordered crystalline structure. That when the rod is pulling up, that the contact surface and the granular plane will densely pack together, so it will cause the upper force which will lift the vessel. And here's our theory, that first we are going to talk about is the packing fraction, which is the total volume of grains divided by the confining volume. So increasing packing fraction and stress will induce the jamming and positive pressure, which based on our intense research, there are three states for this phenomenon, that if the packing fraction is lower than the packing fraction S, and it will be on jammed parts, which we can't pull it up, and in the fragile state, which we also can't pull it up, but in the jammed state, which is the green parts and also the jammed states, that we can all pull it up with the rod. And so we can know that the increasing stress and packing fraction will cause the jamming, since the stress is this on the y-axis. And about the viscous elastic properties of packing there will be three states for the transitioning for the rod. That if we first apply the force on the rod, and it will lead to a initial force change on the granular materials, that later in a very short time, so we can only use log to define it as, so in a very short time it will change into a shear thinning, which the granular material will sliding and cause to our sliding motions, and this part is called shear thinning, and later on they will cause a quasi-static part, which the force chain is completed structure, and we can lift the vessel up. So the packing fraction pi is being used to describe the magnitude for packing, and we also have a formula which describes the strain step smaller. The shear stress is described like the linear viscous elasticity, and here is the shear jamming that we talked about previously. That when it's packed, that the particles will jam together. That it's called a shear jamming. And in the computer simulations, that they will use the discrete elements method, which can lead to the stress tensor on each particle will be relevant to the force vector and also the volume of the system, and most importantly the contact between each particles. And about the force on a stick, that we can, based on our research, that we can lead to a empirical equation which defines the force that we can use, we apply on the rod to lift the vessel as this formula, which was relevant to the most important part of the depth of the rod in vessel, and also the specific weight of the grain, and also the perimeter of the rod, which is like the red one, and also the contact between it. Okay, so here's our theory, then let's move on to our experimentation. First one, we use depth of the rod, which is the most important to do our first experiments. And here we can see from this graph that when we got the depth more deep and the force we need to apply is bigger. And here, because based on our previous theory parts, that we got linear relationship as expected from the equation, and we do 50 experiments for each data point. But there are a big error bar here, so that's why the error bar will happen is because the initial packing fraction can be effectively controlled since it's a complex particle system, so there will be a little large error bar, but it's still in our fitting line. And why of the error bar is because the depth of field of the rod, when the rod gets deeper, the packing fraction in this granular plane will be bigger. So that's therefore we'll have to apply more force to withdraw the rod and lift the vessel up. And next experiment we're talking about the average rise radius of the grain, which we can see from this linear fitting line that it will lead to results. And the mixing with the smaller grain will cause the bigger contact area with the rod, causing a bigger force, which we mix the glass particles and also the rice together. If we mix them together like the 50%, then there will be more, the density will be bigger, so that we need to apply more force to lift it up, since if it's loosen in this two parts, which is 100% of rice and 100% of glass particle. And about next variable, we'll use the diameter of the vessel, which we can see from this graph that the diameter of the vessel will affect the contact plane of the grain layer and the wall of the vessel. That with smaller diameter, the density for the layer will be closer to the vessel and the wall is higher. And so about this error bar is that when the contact, because of the diameter is more intense, that the force chain will not always be ideal in the real situation. So the force chain with a larger diameter, it will need because it's more loosened, so we'll have applied the less force to lift it up. But if it's the diameter is smaller, that in my case we need to apply a bigger force to lift the vessel up, but its error bar is still in the fitting line. And about the explanation of why we use linear fitting, it's because, like this formula shows, that distance for the stress to reach the vessel of the wall will have negative correlation with the stress, as I said previously. That therefore the grain will encounter the different elastic velocity, viscous elasticity property. So that it might cause like the previous graph that. So the distance farther away from the rod will experience a different amount of shear on the particles. So that's why we use that. And about our conclusion, that we can know that we have repeatable setup and with quantified data, and also we have large amounts of data to test these particle systems. And about the conclusion of our experiments, that we use some crucial parameters test that depth of the immersion and will be positive correlated to the force that we need to apply. And about the mix rate will depend on how much it is, and it will depend. The force will like to apply will depend on how much the rate it is. And about the diameter, it will depends on, it will have a negative correlation for the force that we need to apply. So this is all of our report. Thanks for listening.
So can you go back to like the theory part? Right, can you tell us, explain it again?
So there will be 3 stages in the experiments that in the phenomenon that is relative to the packing factor, which is defined by this. And so when the packing factor is smaller by a value, which depends on what kind of granular material it is and other parameters, that it's smaller than this value, that it will be unchained parts, that it won't cause the chaining effect to happen. And so, and also in the middle part between 2 values, that there will be a fragile state that it will also lead to the unchained situation. And about the jam state of green parts, which will lead to there will be for a shear jamming on the particles, which we can lift the particle, lift the vessel up with the rod and or applied force.
Alright. So can you like turn to page 12? Page 11 actually. Like, can you like next page? Yeah, this page. Like, I just want to know like why are those like 2 dots like goes up like that?
So, like, you mean which dots? This 2 dots?
Yeah.
So, as I explained earlier in the report, that error bar will, because the initial packing fraction can't effectively control, because that when you dip the rod more deeper, that the packing fraction under is bigger.
My name is Mia Lin, and our team is called AD1. And today I'm just going to kind of call first purpose. And for the problem statement, is to take a vessel and pour some granular material into it, and for example, rice. And if you dip a spoon into it, then at a certain depth of the immersion, you can lift the whole vessel up and content by holding a spoon. And just basically explain this phenomenon and explore the relevant parameters of the system. And for their main focus, they focus on the relevant parameters such as diameters, grain size, and stuff, and also investigating the relevant parameters. And for their setup, they collect grains and 3D crane vessel, fully devised jug, rod, wood, and sand. And for their theory, they collect a packing friction and spread jamming first on the stick. And for the analysis, they talk about the depth of the rod, average radius of the grain, and the diameters of the vessel. And in the end, for the conclusion, they talk about the depth of the immersion diameters of the vessel, and the whole picture just show a polygon, and also talks about the diameters of the vessel, which shows a negative line, and also the average grain size, which shows also a positive line. And these are just their pros and cons. And for the pros, it got full theory of the phenomenon and got a great data explanation. But for the cons, they lack of experiments set up and explanations. And I think I'm just going to go to the next part. So, can you just turn to page 13? Yeah, and can we just go to backward? As of page 13, you see actually the picture there, shouldn't it be like this, the whole picture? Should be an exponential line?
No, we don't think it should be an exponential line thing. It's relevant to the frictions parameter on the formula that we use. That is not the squared. It's just.
So you think the linear line actually fits?
Yes, we did.
Okay, that's actually interesting because while we're doing our experiment, we actually fit our exponential line. Because don't you think the dots on there, it seems it actually fits more in each other?
But you need a theoretical model to know that it fits on exponential line for accurate. But so do you have any physics model that can explain that you need to fit it in exponential?
I can actually think of it right now, but I don't know because Microsoft just saw that it should have been in exponential line and not in the.
Yeah, maybe that's because there is some deviation because just as I mentioned in the next two dots that it will leads to some error bar that might lead you to think that it might lead to the exponential fit of the experimental results, which the reporter thinks that we should fit it in linear based on our research.
Okay, cool. Then can you just turn to the page that you're talking about, the molecular station, and talk about the spacing?
You mean the?
Yeah. What do you mean that part? The white part?
The white part, which is the red circle, it's because that we don't need to consider this part's force on it because we're discussing, we're investigating on the y-axis force that The x-axis 4 will actually be canceled in our investigation.
And so I'm just wondering, like, is that white space, like, is it like a space?
Because
The white part?
is there, we don't know what shape the space will be, but it's a particle system, so we can't predict that whether there will be a space or will not. It depends on the condition that you are doing the experiment. That there might be some space.
So like you're like not sure like when like every time you put the stick in like what the shape will be, right?
Yeah, we cannot ensure that.
Then like do you think like the space like the size of the space actually matters for like the friction? Do you think
Well,
it matters?
we think the friction will actually matter on the contact surface, which is two sides of the rod. So this space downstairs will only affect if you want to analysis for the x-axis component, that it will need to consider it.
Okay, then can you turn to like the picture like when you're like saying about like the physical device thing?
You mean our experimental setup?
Right. Because like I'm just wondering like can you just kind of draw it out like your device and stuff?
Okay, so let's move on to the backboard. And here will be our experimental setup, which we have a pulley on here and a motor for a constant rotation speed, and it can lead to this part that we fix our rod by the wooden base that I showed on our experimental setup. That the rod and the vessel can be lifted by, here will be a force coach that will measure the force for us. So we can know that the force that we need to pull it up for the maximum value.
Okay, so do y'all just like just use your hand to like pull it?
No, we use a motor, which gives it a uniform rotational speed.
And then like do you think like the angle matters, like the angle that you like insert the chopstick in matters?
Actually, yes, it will matter. So this is why we use that wooden stand, which we can fix our rod in a vertical from the ground, like 90 degrees, that we won't have to consider the x components that much. But there will be deviation because the device isn't always correct. So, but the deviation that I really reported things that we don't need to consider about it.
But how can you make sure that you're like just like staging or not?
Just like you mentioned, that we put our stick inside, and here is a plane that's a metal plane, and here is the fixed part to fix our rod, and we can just measure the as the depth of the rod, that we can just measure this part to get the parameter of the depth.
Right.
Yeah.
Okay, then so y'all like when you like do your experiment, do you actually like change your rides like every time after you do try your
Yes, because the geometry of the rides might be like destroyed, and it will cause another experimental results if we use the same material for next experiment.
Okay, then it's like I'm just wondering like is the main thing that you're like discussing about is the maximum volume, right?
Yes, you need a force to pull it out.
Right.
So we were measuring this value for 15 times to get a experimental data.
Right. Okay, then can you just use like the maximum value to like prove your phenomenon?
What do you mean by proving the phenomenon? That's in our experiments results that we have shown those qualitative explanation that fit our imagination based on theory model. That's, is that what you mean?
Yeah, so you basically just use like, okay, yeah, I think I got it. Then, wait. Like the page 15. Yeah, like then like why does it actually like goes down?
You mean
Like in the middle one?
in the middle one, and that's because when we put only like bigger particles like rice, that the density of this particle system is not that kind. The density is not that kind of big, so it's loosened and our rod can be pulled out more easier. And if we add a smaller particle like glass particle, which fits inside this part, and it will lead to a more bigger density for the particles that we'll need to consider because of the shear jamming, that it'll need to larger force that we'll need to pull it up. So that's our experimental results show us.
But do you think like the materials of like the vessel actually like affects for the friction?
We agree with that because but it only affects this side which particles contact with the vessel. But if we want to calculate the whole force chain, that we will need to calculate the friction on the contact point between the vessel and the materials.
Right. And do y'all do like any experiments on it?
No, that's we fix the value by only using 3D printed vessel, that we can control the friction constants on it.
Okay, then like you mentioned that you guys like shape the vessel before like you do all like this experiments.
Yeah.
Then like why shape the
yes.
vessel but like not like actually like press down the rice to like make it like tighter and stuff?
If you press down the rice, you might destroy the geometry or the rice. And if you shake the rice and that it gets into a volume, which we can use it to calculate our piping friction, which we can in order to control our experiments for more accurate data.
Right. And like, am I right, like you guys didn't use like the same material for like the ball and like the sticker, am I right?
Our stick is a wooden stick.
And the shape that you guys use are like really like.
Yeah.
Great. Then you think like since like you guys are now using the same material, doesn't that like affect the friction too?
Because I don't think that will affect on the friction of the contact. But as I mentioned, as I do the experiments, that we don't focusing on discussing the friction of the rod and friction of the vessel, but that will lead to a different experimental results. So we fix the material of the rod and material for the vessel, but we change the diameter and also like the radius of the grain and also the depth that the rod puts into the vessel. So we're not discussing on the friction of these two things. Yeah. So,
That's probably it.
okay, thank you.
Basically, we just discussed about their chart on the blackboard, because I think like for their page 13, I guess, like they actually draw like a linear line for it. But like in my opinion, like also like our experiment, I think the results actually fits the exponential line more than the linear. And also like we also talk about like does the material actually matters, like they definitely think it matters, but like they didn't actually do like more experience about it. And like we also talk about like the material that they use for like the vessel and the chopstick that's sticking. And basically like the materials that they use are just different, but like in my opinion like they should have like choose the same materials for like the stick and bottle, because I think that will make the results more accurate.
Thank you for the report and code, and I'm the reviewer of this session. So let's talk about the problem statement. The problem statement mentioned that we have to investigate the relevant parameters. So which one of the parameters you think is the important one?
Just as I mentioned in theory, it's the depth of the rod.
Okay, how about it?
Yeah, same. Like actually, like
Okay, so now move on to the theory part. So the first question is that the free body diagram will be like this. So the friction you mentioned is that the friction between the particles and the rod, or the friction between the vessel and the particles.
Actually, the friction we're focusing on is the rod and the particles.
And how about the opponent?
yeah, like because like the thing that we use are actually chopsticks, so we actually focus about like the rise in the chopsticks.
Okay, so could you please answer what's the direction of the friction?
The direction of the friction will be varies from the contact point between, but I think if we put a force on it, and it will cause a downward friction.
And how about opponent?
Yeah, I think when we like actually like insert down, like the friction actually goes up, like just for like the rise.
Okay, so since the report mentioned about the force chain, so could you please explain what is the force chain briefly?
Force chain is that multiple particles that get together and get a higher density, that it will cause the force to like line up for one
Okay, how
chain.
about opponent?
Wait, can you just like explain like?
Can you briefly explain what is force chain? Do you agree with the report?
Yeah.
Okay, so do you think the force chain should be parallel to the ground or not?
No.
And how about opponent?
I also think that it shouldn't like parallel with the ground.
Okay, so when will the force chain happen? Is there a situation?
The force chain happens as our theoretical models that if we give a force onto a rod, it will start to have initial
Okay,
force
how
chain.
about opponent?
Yeah, I think also like that.
Okay, so now move on to the experiment part. So you mentioned you have two kinds of the particles, right? So if you change the particles, the mass of the particle and the volume of the particle, and also the space between the particles will change, and the friction. So which one do you think is the most important?
Oh, well, we also think that the friction.
And how about
Also friction.
So do you think the mass, the change, and also the space between the particles won't affect the result?
Actually, I think like the space between like the right actually affects the results because like.
Okay, so how about a reporter?
Oh, we also think that's will affect.
Okay, so so what caused the please turn to page 20. So the error bar here is really long. So what do you think is caused the big error bar?
We think that it's because the rise when we pulse might be destroyed, and also because the diameter is too small, that the force will be too.
Okay, got it. Okay, thank you for the reporter and the opponent. I'm the reviewer of this session, and I'm going to review question number 12, rice kettlebell. And here's the problem statement. We main focus on at a certain depth of the immersion and also the relevant parameters. And the test fulfilled is partly fulfilled. And here's the summary of the report's presentation. So they main focus on the boundary of the model and also the maximum friction and also relevant parameters that answered in the short question, reverse short question. And the theory they used is the first chain. However, they didn't explain the first chain and also the packing friction and also the viscous lengthening of proportions and also the shear jumping. And the setup they use is variety of the container and variety of the rod and also the force figure and the 3D print vessel. And for the parameters they did is the diameter of the vessel and also the depth of the rod. And here's the conclusion of the presentation is that initial packing friction can't avoid and also this smaller grain will cause big force and smaller diameter of the vessel when they are higher. And also the depth of the immersion either would have the linear relationship. So here's the pros and cons of the reporter. The pros is that his well explanation of the phenomenon and also quantitative to analysis. And the setup is really reusable. And how about the cons is that they didn't explain the theory in detail. They didn't explain what is the first chain while they mentioned it in their report. And also unclear understanding of the problem statement. They didn't explain the condition that the first chain exists and that they found boundary of the model that the reviewer thinks is pretty important to find a boundary. And also didn't explain well of some of the error bars since it might be out of the boundary limit, so it caused a big error bar. So here's the pros and cons of the opponent. So the opponent points out the parameters that are important, but the report didn't matter. However, the cons is that it didn't discuss about the error analysis of the reporter that the reviewer thinks is pretty important. And here's the discussion point of the opponent and the reporter. The opponent asked about the friction seems to increase exponentially, so why do you fit the result as a linear equation? And the reporter answers that according to the model we provide, it should be the linear equation. And the reviewer thinks maybe the condition that the reporter considered has out of the boundary limit of the model, so it will have this kind of phenomenon. And the next discussion point is the blurred area of the reporter's graph matter and friction. And the reporter answers that depends on the contact point on the slide. And the reviewer thinks the friction that the reporter talked about all over the presentation is the friction between the rod and the particles. And the opponent asks, do you measure the friction coefficient of the particles? And the reporter says, no, they didn't. The reviewer thinks the friction coefficient is one of the most important parameters. And also, the next discussion point is, the opponent asked, will the angle affect the result? And the reporter answered yes. So if the rod isn't vertical, it should be considered a component of the friction. So here's some missed point the reviewer would like to mention, however the reporter and the opponent didn't mention about. So the reporter talked about the first chain, however didn't explain it. And since the reporter provided a model of comparison with the results, the trend of the experimental results didn't show agreement with the assumption. And didn't consider the friction between the particles to the vessel. They just consider the friction between the rod and the particles. And they changed different particles for the experiment, but it changed the density friction coefficient at the same time. So we don't know which kind of the parameters is that the most important, and also they didn't mention about it. And the reporter has wrong analysis of the direction of the force. We think the friction should be friction that we pulled up the vessel should be up. So here's the missed point that reviewer would like to mention. And thank you for listening.
Here will be my reporter's concluding remark. First, I want to mention is about experimental that we'll need to we have investigated about parameters of the depth of the rod and average radius of the granular material and also the diameter of the vessel. But we didn't consider about the friction of the rod and the vessel which contact with, although we fixed them through the whole experimentation, but that should be also be in our consideration. That is a good point that raised by the opponent, which we'll do in our future work of the investigation. And about the theoretical model that We use tracking correction and also viscous elasticity of granular objects and also DEM model and empirical line to explain our model. But there is something that the reviewer points out that the direction of the friction and the direction of the force change might need to be considered and explained, which we think we can do in a future work, like using simulation or something. That also we'll need to explain more about how to form a force change, which is formed that we apply the force on multiple particles that will force a force chain which is lined up, and because of the force that we put on the particles. That here is whole of my remarks. Thanks for your kind attention.
Okay, so I have a question for all of you. So since the reporter used two different materials, one is flexible and one is dry. So how can you define the grain size and also the packing of the material?
Since that we can know the relationship between them and do some calculation if we do future work on the measurement of them, but we can know a tendency of what it will be in the experiment.
So, I believe it depends on the particle's volume over the vessel's volume.
Okay.
Yeah, like mine's not like the reverse.
And reporter, please turn to 13. Okay, on the right, your pressure seems not depend on the vertical position. But when you learn in high school physics, in fluid, the pressure should be increasing. Increasing when you go deep to away from the surface. But here, it is a granular material. Do you have any simple physics argument of why the constant pressure can be used?
The pressure will be calculated due to the depth of the rod. So we think we can see it as a complex particle system and apply the pressures formula into it. And so as the rods go deeper and the pressure at that place will be bigger, so which leads to the results of these two experimental data.
But you say when the force is in linear relationship with the height, so the pressure you used here is a constant.
This is I think we'll do it more on the research because we get it only from a intense documentary research. So maybe we can change the theory model in the future, which relative to the height of the pressure.
I have a related question. So the force here, so this figure tells you that if you apply a larger force, you can go deeper into the material.
This formula tells us that
Not the formula,
the data tell us that if we put more deeper the rod, then we need to apply more bigger force. It's dependent on the depth of the rod.
the force to lift it up or the force to push it down.
To lift it up.
When the kettle is in the air, the force should be equal to the mass of this cathode.
So there will be some boundary conditions to the depth of the rock that we haven't calculated or do experiments to prove it.
I think the real problem is in this problem they seem to ask you about the critical depth of the spoon, beyond which you can lift the cathode. So is there some critical depth in your data?
Based on our data, that those depths that we use to do the experiments can be measured and can lift the vessel up. Yeah. They can hold the vessel up. So we do more research on the force investigation.
Okay, so great for the report is 5, 6, 7, 5, 7, 6, 7, 7. So for the opponent, 5, 6, 7, 6, 6. And for the reviewer, 8, 7, 8, 8, 7.